Hello everybody, welcome to the lecture on limits at infinity and asymptotes. What I have here is an informal definition that talks about the limit at infinity, and then it's followed by a definition that is formal for horizontal asymptote. I want to illustrate this definition using this set of graphs here. The first graph shows you f of x as the blue function. And the blue function is traveling, and then it seems to run very, very, very close to this orange dashed line. This orange dashed line happens at capital L. So as you can see the function trailing very close to L, we are using this idea in terms of limits at infinity to define horizontal asymptote. Well, you understand the horizontal part of it, right? The asymptote kind of shows us where the function is limiting. Okay? In some situations, the graph can cross over a horizontal asymptote in certain circumstances, but typically we see that the function will trail very close to that asymptote or the horizontal dashed line. It's dashed because it's not part of the graph. It's an invisible line that you are able to see where the graph trails very close and does not touch it. So in this case, if you looked at f of x and you looked at the x values, these x values are going endlessly, right? They are going towards positive infinity. So as your x approaches positive infinity, this function f of x, this approaches, or this function is getting closer and closer to this value L. So as x approaches positive infinity, f of x approaches a specific number, a value L. That L is the place where you will draw the horizontal asymptote. And likewise, if you looked at graph B, the function f of x is happening here. And as we can see, the graph is trailing very close to this horizontal dashed line that's passing through M. If you investigate once again, the x values are decreasing in this direction, right? So as we approach negative infinity, or meaning as the x values approach negative infinity, they get very, 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 very small. As we look at those very small x values corresponding to those very small x values, your f of x seems to be trailing very close and getting closer and closer and closer to this value m. So f of x approaches m. So we can see once again that for these limits at infinity, be it x approaching positive infinity or x approaching negative infinity, the f of x, the function, approaches a finite number L or a finite number m. It could be anything, right? So that's a finite number. And the definition here says, if limit f of x as x approaches infinity equals L, or if limit f of x as x approaches negative infinity equals L, okay, whatever be the value, then we say that the line y equals L is a horizontal asymptote of f. That is what we have here. And as always, there must be dashed lines to indicate that they are not part of the graph, because if they were part of the graph, then that's a bit confusing there, right? You have the f of x, which is a curve, and then you have this line. So to differentiate that we're actually highlighting the invisible horizontal asymptote, we use the dashed line. And I had mentioned that sometimes the function can cross the horizontal asymptote. The rule is very strict for vertical asymptote. Vertical asymptote typically is where your denominator, or typically where your function gets undefined. And so it is typical in a rational function where the denominator becomes 0 at certain values. And where it becomes 0, we draw the vertical asymptote. And there is no way for the function to cross. It can never cross the vertical asymptote. But here in this example, you can see that the function actually crosses the horizontal asymptote many times, okay? Infinitely many times. So this is a funny function, cosine x over x plus 1. And so for these kind of rare situations, Here we could come up with a horizontal asymptote at y equals 1, but the function seems to oscillate up and down around 1, and its amplitude, right, the height of this wave pattern, kind of reduces and gets closer and closer and closer to the value 1, right? So the function seems to kind of run very almost, trying to coincide with the horizontal asymptote. So this was just an example of how there are cases, rare cases, where we can find a function behaving differently when we have a horizontal asymptote. It can't touch it. Does not mean that it should never cross it. It'll mostly not cross it, but there are times like this where it can. And we've also seen, other algebraic limit laws. We've seen squeeze theorem that apply to limits of functions. And these limits at infinity are still good for those laws. And so we can apply those laws in circumstances where we allow x to approach infinity or negative infinity. Now let's take a look at this example, computing limits at infinity. We have 3 questions here, A, B, and C. For each of these questions, we're asked to evaluate f of x as x approaches infinity and the limit of f of x as x approaches negative infinity. And they want us to determine the horizontal asymptotes for these. Let's start off with part A. F of x equals 5 minus 2 over x squared. They want us to find the limit of f of x as x approaches infinity. Well, we have to discuss both infinity and negative infinity. Let's start with positive infinity. We're technically trying to find or replace this f of x with this given expression. And we can use the algebraic limit laws, which allow you, the sum of limits, the constant multiple rule of limits. So, the things that we've seen before. So this allows us to separate them out by the difference law of limits. Now notice how limit of 5 as x approaches infinity. If you look at this, this is just a plain number 5. There is no x, which is the variable we're interested in. There is no x that is involved in that expression, and therefore, no matter what happens to x, whether x approaches infinity or not, it's going to remain constant at 5. So we have 5 as the result of limit 5, a limit of a constant. That's the constant rule. And then here, you can reason out that, as x takes a very, very, very large value, what happens to the x taking a very large value in the denominator. Okay, you can not worry about the square, actually, because infinity squared is still infinity. So 2 over infinity is what you're trying to do. Now, infinity is a very, very large number, but when it is sitting in the denominator, right, its value becomes, the value of the fraction becomes really, really, really small as in it gets very close to 0. Okay, so we can illustrate that way and then say minus 0, or you could use the limit laws like this, where I pull out the 2 and I separate the x being multiplied. This can make it even clear, more visible for you to actually see that as x approaches infinity, 1 over infinity is 0. Another way to kind of recall this is you can think of infinity as something over 0, right? Never divide by 0 because that makes it undefined. Just for convenience, I'm writing it like this. Now, there is nothing like infinity equals like this, right? I'm just giving you some kind of a hint to kind of imagine infinity to be like 1 over 0, okay? So imagine infinity is not a number. So I'm not trying to tell you that it's a number. I'm just trying to help you see what I mean when I say 1 over infinity is what you're trying to do, right? With 1 over x. So you're basically doing 1 over infinity. But if you think of infinity as 1 over 0, right? If you use the reciprocal property, That's basically 0 over 1, which is 0. So when you have infinity sitting in the denominator, the effect of that fraction actually takes it to 0. So this also becomes 0. So 2 times 0 is 0. So you can reason out, or you could work it out like this to figure out what happens with 1 over x when x approaches infinity. And then, so clearly that's going to be 5 minus 0, which is 5. So what I'm getting is limit f of x as x approaches infinity is 5. Well, we could make a similar argument for negative infinity. So I'll just say, similarly, limit f of x as x approaches negative infinity is also coming out to be 5. Okay. You can work through the problem the same way, right? Negative infinity. Negative infinity, you can think of it as negative 1 over 0, right? You still get the same effect, that the result comes out to be 0. And so that is why I just did it thoroughly for 1. And where you can reason out similarly, you can use that argument to simply state the obvious. All right, so now I have these two. What does that mean? Well, let's take a quick look at the definition. The definition told us that if the limit of a function as x approaches infinity, or as x approaches negative infinity, or both, right, if they point to a finite number, then that is where you have a horizontal asymptote. And if we come down to our problem, we have proved that, in fact, both for the negative infinity portion as well as for the positive infinity portion, the the limit points to a finite number. Okay, so this is a finite number. Finite number. That means we have, this implies, the horizontal asymptote occurs at, this is a horizontal line, so it has to be y equals this number 5, okay? Or because we're using f of x, you could call it f of x equals 5. So that means you know where to draw the horizontal line. You draw the horizontal line through 5. If you are curious, which I hope you are, when you draw the graph of f of x, which was 5 minus 2x squared, it actually comes out like this. And you can see how the left end of the graph, this comes out as two branches because it's a rational function. When it branches off on the left, you see that the left end of your graph is actually, as x approaches negative infinity this way, it trails very, very close to 5. So your f of x approaches 5 as we approach negative infinity. And as x approaches positive infinity, this is the right branch of the graph, we have the function f of x approaching 5, this horizontal asymptote. Now that concludes our response for question 1. We move to part B. Part B was to find the limit, once again, for f of x equals sine x over x. So let's write that down here. B was f of x equals sine x over x. So we're asked to find limit x approaches positive infinity f of x. And that's going to be limit of sine x over x. Now when you see these kind of things, especially trigonometric function like this over x, you should be able to recall squeeze theorem, because in fact there's a specific relation that we get from squeeze theorem. If you quickly recall squeeze theorem, it said that if we can't find the limit of a particular function right away, but instead if you could find two other functions, right, one above it and one below it, squeezed in between this given function that you find it difficult to obtain the limit. So if we can find two other functions above and below it that can squeeze it in between, and if they're pinched at that point where we are looking for the limit, then the limit of the other two functions would be an indication that the function that's caught in between would also have to have the same limit. So you're squeezing this in between so that they can all line up. So using that concept, what we see is we take the sine x over x, okay, and we're trying to, oh no, hold on. We want to actually talk about sine x itself. In order to utilize the squeeze theorem, we need to try to see what are those two functions you can find that will squeeze this in, right? So we want something that will squeeze this function from above and below. So we can't right away have a visual of such functions. So we'll always start with very basic information. Basic information we have is sine x, right? Sine x, because it's because of the position of the function in a unit circle, sine x can take only values between -1 and 1, isn't it? Yeah. So all other values will be fractional, right? So they will stay within -1 and 1. So this is a basic trigonometric fact for a unit circle. Using this fact, you want to make this match up with the given function. So the given function has an x, the sine x divided by x. So because of this inequality notation, we can actually divide by x on all three parts. Now notice that your middle portion, the middle part actually is your f of x. So now we can talk about having found a function on the left of sine x over x and a function to the right of sine x over x. Okay, so which means you found sine x over x to be squeezed between -1 over x and +1 over x, right? And these two are actually rational functions, right? -1 over x, we in fact know how that would go. Now we apply limit on all three parts, okay, to kind of show that application. I'm going to use colors, and so bear with me. Got this. And again, we are interested in just doing one part, the one side, x approaches positive infinity. And then we will see if we can think along those lines for negative infinity. So I've applied limit on all three parts, right? So up to now, we've used algebra to help us bring to this point, and now we are using calculus by applying limit on all three parts. We just discussed about what happens when I have infinity, when x takes a very, very large number in the denominator, right? So it becomes 1 over 0, so that 0 goes on top, so this whole thing will become 0. So we can just say this thing approaches 0, and this thing also approaches 0. I'm not canceling it, I'm just saying it's approaching 0, because the value for this will be 0. So in that sense, I'm going to rewrite this as 0 less than or equal to limit x approaches infinity, sine x over x less than or equal to 0. Look at this mathematical statement. Okay, this quantity in the middle is both greater than or equal to 0 as well as less than or equal to 0, right? So this statement can only be true for 0, isn't it? It can't be both greater and lesser than 0. But you see that equals bar there, less than or equal to, less than or equal to, that is the key there, right? Otherwise, it would make it a false statement. So because of that equals bar, this is a true statement, and this basically is your squeeze theorem. You're squeezed between two numbers that are the same, which means the only way we can justify it is that the middle portion is also equal to 0. So this implies by squeeze theorem, another name for squeeze theorem is sandwich theorem. So this is sandwiched between the two numbers that are identical. By squeeze theorem, limit sine x over x as x approaches infinity equals 0. We just found a limit for this trigonometric expression. And what this means then is, because is this a finite number? Yes, it is. This is a finite number. What's wrong with 0? Nothing wrong with 0. It's a perfectly fine number. So because it's a finite number, this implies there is a horizontal asymptote at y equals 0, right? And remember I told you, you can write it as y equals 0 for quick recognition as to where it passes, but this is the same as f of x. Y is the same as f of x. And what actually is y equals 0? So you're drawing a horizontal line that passes through 0. What is that horizontal line? Horizontal line in this case is your x-axis. I will just say horizontal asymptote coincides with the x-axis. Okay. If y equals 1, you know it is 1 unit above 0, so you're going to draw a horizontal line at 1. But when it is at 0, it actually coincides with your x-axis. So we were able to find a horizontal asymptote for this given expression using squeeze theorem. In order to use squeeze theorem, we started off with a very basic trigonometric relation as sine x lies between -1 and 1. And we use that relation to actually build up our a middle portion that resembles f of x. And then the whole idea was to show that the left end, the left part and the right part, both approach the same value when you take the limit. And because of that, we now have squeeze theorem applicable. Okay. What I should also discuss is that this is going to be the case with negative infinity. Okay. So I forgot to mention that. So let me just put that somewhere here. Let me squeeze that in there, if you catch the pun. Similarly, limit sine x over x as x approaches in negative infinity, that was the whole point, equals 0. Okay. So we get both sides approaching 0. So we will have our graph actually hovering around or trailing very close to the x-axis. So let's see if that's what is justified in the graph. So the graph then would look like this. And this is again another classic case where the horizontal asymptote actually coincides with the x-axis. So we couldn't do the dashed line over it because then we are kind of saying, oh, there's no x-axis, right? Because dashed line means it's not part of the graph, but this is part. It's coinciding with the grid itself, and so it's not indicated to us here. But as you can see, the horizontal line or horizontal asymptote coincides with the x-axis, and it's kind of visible with the graph of sine x over x. It's actually crisscrossing. It's oscillating about the x-axis, which is a special case where your graph could cross the horizontal asymptote, but the behavior is that this graph is actually going to a value very, very close to 0. Same happens on the left side as well. So both sides behave the same way along the horizontal asymptote. Now our third problem is a little more tricky because it's asking us to find the limits at infinity for tan inverse of x. Tan inverse. That looks a little more complex than what we're used to. So let's take it apart slowly. Now tan inverse of x is a very simple function comparatively because this is something we've learned in trigonometry. So we in fact have a visual of this graph also from trigonometry. But let's explore it from what we are familiar with, the tan function, the graph of a tan function. To answer this question, let's take a look at the regular tan function. So tangent x looks like this, right? It's going to be this repeated pattern between two vertical asymptotes, right? This is just for one period, and so this is how it repeats. So what you see is that you have a continuous piece of this tangent x happening, this blue graph, running between this x equals negative pi over 2 on the left, the orange dashed vertical line, and x equals pi over 2, the blue dashed vertical line. So it's between these two that you have this blue function traveling. Now, if you looked at this kind of limitation, clearly the vertical asymptote is a strong limitation, and the blue graph is not going to cross over to the right or cross over to the left of these two vertical lines. Now, using this information, we can quickly recall that tangent x, in this case, we can write it as an inequality maybe, is negative pi over 2, right, less than tangent x less than pi over 2. You can write this limit on the tangent function for this one period. So what that means then is limit of this tangent x as x approaches, right, when your x value gets closer and closer to this value, negative pi over 2, right, your tangent function, what happens to your tangent function? The tangent function actually goes to, this is on the left, right? So the blue function actually goes towards negative infinity. And when you take the limit of the tangent function as you approach x towards pi over 2, okay, that is this right side, as we get closer and closer to this value pi over 2, we notice that our tangent function, the blue graph, actually goes up indefinitely. So that's going to be positive infinity. So we're going to use this idea to actually talk about tan inverse. Okay, now if you already are familiar with tan inverse function, that's great. Okay, but if not, we can use this as an argument to see how the tan inverse function will work. Now, tan inverse is when your x and your y coordinates get interchanged, right? That is the inverse function. The x and the y will get interchanged. So based on that idea, then we can let me maybe show it here. Okay, this implies limit, okay, when x approaches negative infinity for tan inverse of x, right, negative infinity. So then what happens is this is going to approach negative pi over 2, right? And for the second piece, as x approaches infinity, right, these two get switched. So tan inverse of x will actually approach pi over 2. Now notice how the limit actually approaches a finite number up and a finite number here. In this particular case, they do not approach the same value, right? For the negative infinity piece, it's actually a horizontal asymptote is going to pass through negative pi over 2. And for x approaching positive infinity, for the tan inverse function, the horizontal asymptote will be pi over 2. So it is possible to have two horizontal asymptotes, as in this example. So when you actually look at the graph of tan inverse of x, your tan inverse of x will be trapped between these two horizontal asymptotes, passing through negative pi over 2 on the bottom and pi over 2 on the top. Next, I want to discuss about the possibility of a function having infinite limits. Okay, so maybe I'll just write it here as infinite limits. Okay, so limit f of x as x approaches, let's say, positive infinity. This itself could give a value that turns out to be not a finite number, but it could end up as infinity. We call it as infinite limits. And you can also have limit f of x as x approaches negative infinity to produce negative, positive or negative, it doesn't matter, right? Likewise, you can have the other possibility of limit f of x as x approaches infinity could produce negative infinity as the answer, and limit f of x as x approaches negative infinity could produce positive infinity. So you have these four options, right? So because four options for the four directions, right? Four ends. So you have as x approaches positive infinity, right? You can get an answer as either positive infinity or negative infinity. And likewise, when you have x approaches negative infinity, your answer could come out to be negative infinity or positive infinity. So we have these four possibilities. Okay, so there is the language that says limits at infinity, which means we are actually looking at this portion, right? At infinity, so going towards infinity. And then when we say infinite limits, that means the answer involves infinity. Okay, so limits at infinity means that x approaches infinity or negative infinity, but infinite limits would mean then that we are getting an answer. The limit answer is not a finite number. Instead, it turns out to be an infinite limit. So what we can then see is that limits at infinity helps us to find the horizontal asymptote, whereas these infinite limits actually help us to discuss the end behavior of a graph. So I have that information out here for us, the end behavior of a graph. Now, we are looking at the ends of our graph, and therefore we are allowing our x to approach either infinity or positive infinity to see as we get further and further to the right or to the left, what is happening to the ends of the graph. So this discussion here, or these kind of pointers here, tell us that if the function f of x approaches a horizontal asymptote, y equals L, that is one of the ways we can understand the end behavior, right? Because the ends of the graph are trailing very close to the horizontal asymptote. Sometimes the ends of the graph could branch off either towards positive infinity or negative infinity. That's the second point. The third point says maybe it does not approach a finite limit, right? It either approaches a finite limit or an infinite limit. And you could have a situation where it does not do that, where it does not approach a finite limit, it does not approach an infinite limit. Instead, it can have some kind of an oscillatory behavior, okay, where we've seen that it is kind of bobbing up and down, but it's not really settling in on a particular number or a particular direction. Some of the common end behaviors that we see can be predicted in polynomials, okay, or power functions. So polynomials, we know by the family of functions that it falls under, that these are functions that are continuous. There will be no breaks. You don't expect any vertical asymptotes, in the presence of such asymptotes in a polynomial function or in a power function. So because of the stability of these kind of functions, all it takes for us then to, when we discuss about end behavior, is only to look at the left end and the right end of your graph because they go endlessly. So now we are looking at, a crisp notation for power functions. So if you have x power n, your end behavior would behave in a certain way, meaning it either goes towards the positive end, towards positive infinity or negative infinity, depending on your given degree, okay, the degree, the power n. So let me just discuss that. Now, this, this color. Now, this x approaches positive infinity means we're talking about the right end behavior. And x equals negative infinity, that means we're talking about the left end behavior. So what we're saying then is that if you are looking at a polynomial, right, a polynomial of degree 1, x power 1, which is basically x, right? f of x equals x power 1 is basically x. It's going to be a line, right? So which means the left end of this line goes towards negative infinity because it's going downwards, and the right end of your line goes towards positive infinity. And if you kind of compare these two, right, as x approaches positive infinity, your function also approaches positive infinity when n is 1, right? And if you come to this one, as x approaches negative infinity, when n is 1, the function also approaches negative infinity. As x approaches negative infinity, your f of x approaches negative infinity. That's for a line, okay? Now take degree 2. Your f of x is now x power 2. When your degree is 2, right? So at the left end as well as at the right end, you notice how your function, both ends point upwards, right? So upwards as in it's going positive towards positive infinity. So your limit approaches positive infinity as x approaches positive infinity. Your limit of f of x approaches positive infinity as x approaches negative infinity. So that you come back here and compare that behavior. So when n is 2, right, the degree, the power is 2, your limit is positive infinity. Likewise, when n is 2, the degree is 2, the limit is positive infinity, whether it's the right hand or the left end. So both ends are pointing in the same direction, and they both are positive infinity, right? Then the third one is a chair-shaped graph. This is of degree 3, right? The degree is 3. This is the left end, and that's the right end. So as x approaches positive infinity, the right end of the graph is positive infinity. As x approaches negative infinity, the left end of the graph is negative infinity. We'll come back here and observe the behavior for 3. The 3 right end behavior says it's positive infinity. Is that the case? Yes, it is. And then between these two, these are for even numbers, these are for odd numbers. So when our degree is odd, 3, the left end behavior is pointing to negative infinity, and that is the case. So you can actually, looking just at the degree, not even looking at the graph, just by looking at the degree of a power function, we can decide how this works. Now these are for power functions, and as an extension, these can be used for polynomial functions where you look at the leading coefficient, right? So for instance, if your polynomial function, say, had 5x cubed plus 3x squared minus 2x plus 11, something like this. What we're saying then is, even though this is not a power function, it's a polynomial function, you just look at the leading coefficient and just look at the behavior, because this is going to be the dominant term in this polynomial. So the leading coefficient is always the term that contains the highest degree. So among the other terms, this is the term with the highest degree. The degree is 3. And therefore, the function, the graph, will behave according to this. And if the degree is 3, we just saw that the left end will approach negative infinity, and the right end will approach positive infinity. Right? So you kind of can tell how the end behavior will be. Okay. And there is, of course, something we learned in algebra, which is if your leading coefficient had a negative sign, right? This is with positive sign. If there was a negative sign, then everything changes, right? If there was a negative sign, then this gets flipped. So the left end will be positive infinity, and the right end will be negative infinity. So we can get a lot of clues algebraically to discuss the end behavior. But here we're using calculus to discuss about the end behavior, because we're kind of talking about the limits. What happens when you are looking at a rational function? A rational function contains the word ratio in it, which means it's going to appear as a ratio. A ratio of what? Ratio of polynomial. So it's going to be a polynomial over a polynomial. Okay, a standalone polynomial, we have a way to learn about its end behavior. But when you have a rational function, we have some extra conditions to pay attention to. Whenever you have a ratio in math, we want to make sure that the denominator is always non-zero, right? So your q of x must not be equal to 0, because that's when it makes it undefined. Okay. So to be smart, we have to see where will it become 0. What choices of x will make the denominator 0, so that we can kind of avoid them or exclude them, or at least know what happens. Now in algebra, we used to exclude them from our domain. Here too we'll do that, but then we are actually here in this particular section interested in the end behavior. So we are interested in knowing where the denominator becomes 0, because where it becomes 0, we're going to have vertical asymptotes. Vertical asymptotes means your graph cannot cross over to the other side of that vertical asymptote. Now, clearly, that will create a divide or a break in your graph. So your graph is going like this. I mean, it's looking more like a wave pattern, but say your graph is going like something like this. And then if there is a vertical asymptote, there's going to be a break. So your graph cannot behave that way, right? Your graph has to behave a certain way. Let's say, okay. So let's say your vertical asymptote is here. Your graph could possibly behave like this on this side of the asymptote, and could behave differently, right? Oops. Differently on the other side of the vertical asymptote. So we don't know how it's going to behave, because there is a break. Now you no longer have one continuous flow of a graph. You have a graph that's cut off, that therefore giving us how many ends? We will now have 4 ends because we have 2 branches of that graph. The graph broke off into 2 parts. Okay, so then that can be discussed again via algebra, because algebra again gives us a few hints. Okay, so algebra tells us, well, if you had a situation like that, then we can use algebra to very quickly decide what's happening. Okay, so how do we decide that? Now, well, we have to compare the degree of the numerator and the degree of the denominator. That's the whole theme here. So if the degree of the numerator, in this case, the degree of the numerator is n, and the degree of the denominator here is m. So you are comparing them, and we're saying if n and m are same, if n and m are same, let's say degrees 2 up and 2 down, then we can be assured that there will be a horizontal asymptote at a value that is obtained from taking the ratio of the leading coefficients. So if these 2 degrees are the same, then you're taking the number that comes in that term on the top divided by the number that comes in the bottom. So I'll just give a quick example of that. Okay, let's say your rational function was 3x squared plus 2x minus 4 divided by 7x squared minus x plus 12. Okay, something like this. So here we are interested in comparing the degree. The degree is the same. We're looking at the first condition, right? So n equals m. So the degree is the same. If that's the case, then what we're assured is that there will be a horizontal asymptote at y equals an over bm. So what does that translate for us? For us, we're going to have an asymptote, a horizontal asymptote, at this 3 over 7. So 3 over 7 is the number where you'll draw a horizontal dashed line, and you know that your graph will have this, will trail very close to this horizontal asymptote. How easy is that? Like, you're not really doing any big computation. Well, there is an algebraic way to do this, which is this, and there is a calculus way to do this, which we will look at shortly. Okay, but it's always calculus way of doing will always be superior, in terms of all the sophisticated ways to do things. But remember, we always do algebra before calculus. So if you can solve your problem via algebra, better. Okay, it's just going to save you the trouble of doing extra computation. Okay, so now we have all of this for condition 1. So I'm going to erase all of this. Now let's talk about condition 2. Here they're saying, what if the degree of the numerator is less than the degree of the denominator? Okay, let's make this 3. Okay. So the degree of the numerator, n is less than m, 2 is less than 3. If this is the case, there's a straightforward answer, no computation, nothing. You can be assured that the horizontal asymptote will be on the x-axis. The degree of the numerator is less than the degree of the denominator. Okay, then we know we can assure this by that there is a horizontal asymptote. Okay, very easy. Okay, Now let's go to the third condition. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Okay. The limits at infinity are either positive or negative infinity, and it depends on the signs of the leading terms. And then we also have to do long division, because if you can write the function like this, right? When you do long division, you will get a function. And if your long division gives you an expression like this, then you can say that there is an oblique asymptote, right? If this g of x was a linear function. Okay, let me quickly highlight and then continue my discussion on that. So if the degree is exactly one more, then we have an oblique asymptote. Okay, all right. So what we're saying is the degree of the numerator is bigger than the degree of the denominator, no horizontal asymptote. Okay, we need to do a little more research is what they're saying, but there's not going to be a horizontal asymptote. However, if you were able to do long division and come up with an answer that provides a linear function here, right? So this is going to be linear, and then this is like your quotient remainder over divisor. Remember that? For mixed numbers, this is what we do. So this is similar to the mixed numbers, just that it's all happening in polynomials, right? So this quotient, meaning the result of it, if you get that as a linear function, that function tells you that there is an oblique asymptote. So if you graph that line, that will be your oblique asymptote. And this is usually the case when we have the degree of the numerator, right? If this n here and this m here, if this n was exactly one more than m. So if m was 2, this must be 3, because this is exactly one more than the m, then you can expect this linear setup. Or if this was 5, then this must be 6, right? So this numerator, the degree of the numerator was one more than the degree of the denominator. This will happen. If you think about it, yes, the degree will be one less, producing a linear function. Okay. So these are all oblique as in slanted. Okay, horizontal is of course horizontal. So oblique means slanted. So when there is no horizontal asymptote, there could be a slanted or oblique asymptote, provided the degree was behaving in that manner where it was exactly one more. Okay, so all this is algebra, folks. That will help us to understand the presence of asymptotes, the behavior at the ends, the end behavior, and how to handle rational functions without having to get too deeply involved in computation. So if you can remember these hence, we avoid computation. Let's take a look at this example. We are asked to find the limit of f of x as x approaches infinity. Okay? This is for power functions. Now, we can approach this via algebra, so let's just do that by the side. But they're asking us to use calculus because it's a calculus class. We're going to do it via calculus. However, let's just do the algebra just to have a preview of what the answer could be, right? So if you have to go back to the chart, you can always pause the video and go back to the chart, or you can go to OpenStax and look at, follow along with the book. So we have, for the first problem, right? We have negative 5x cubed, negative 5x cubed. So you're going to look for two things, okay? So you are going to look at the degree is 3, and you're going to look at the sign of the leading coefficient, which is negative. Okay. If the degree is 3, according to the conditions, the left end, so we're talking about the left end and the right end, right? The left hand behavior and the right hand behavior. So typically, if the degree is 3, the left end will be of the function will be pointing towards negative infinity, and the right end is positive infinity. But because of this negative sign, right, this will have to get flipped. So that means this goes here and this goes here. So the left end will be upwards, and the right end will be downwards. So your graph will be something like this. It can look definitely different. right? It could be like this also, but I'm just talking about just the ends, right? This end and this end. This end will be, the left end will be pointing upwards towards positive infinity, left end pointing downwards towards negative infinity. So now let's test that via calculus. So limit f of x as x approaches, let's start with positive infinity, will be, this is a, we're doing a, limit of negative 5x cubed as x approaches infinity. So I'm pulling out the negative 5. So limit of x cubed, x approaches positive infinity. So that's infinity times infinity times infinity, right? It's all the same. So it's going to be negative 5 times positive infinity, right? Yeah. So that actually turns out to be negative 5 infinity or something like that. But what is 5? Nothing, right, compared to infinity. However, you're multiplying infinity by a negative number, right? Therefore, that comes out to be negative infinity. Now, x approaches infinity is a right end behavior. So this is our right end behavior. A quick check on our algebra verification. Yes, our right end after the flip gave us negative infinity. Likewise, you're going to now discuss about the left end. So that's going to be limit negative 5x cubed, x approaches negative infinity. Once again, I pull out a negative 5, limit x cubed, x approaches negative infinity. Okay. Now, here again, you have to reason out. It's a very, very, very small number, right? A negative number. So it's going to be a very small number. So it's a negative number, which is raised to the power 3. So negative times negative times negative. So it brings back a negative number. But because it's a very small negative number, this comes back as a very small negative quantity. Very, very, very small. So it's negative infinity. Now, if you look at the multiplication here, it's about the sign, right? Really, 5 times infinity doesn't, a small number 5 does not make infinity any different. It's still infinite. It's really the largest. But then with a negative times negative, it makes it positive. I'm just for emphasis putting the plus. So it's positive infinity. And this is your left end behavior. So that kind of gives you a sense of how the sign will change or how it will behave with the infinity or the negative infinity and the compared with the power. Okay, so you notice how our algebra gave us a quick results, but calculus was more sophisticated. It still gave us the same results. Okay, so you can do similarly for part B. I will just discuss the answer for that. Okay, so for this one, notice how you have the degree is 4 and the sign is positive, right? Positive 2. So we're only interested in the positive sign. So that means both ends are going to point, because it's degree 4, you could expect 3 turns, right? All this from algebra. Okay. So both ends are going to be pointing upwards. So the left end behavior will be positive infinity, and the right hand behavior will be also positive infinity. So this answer will be positive infinity, and this answer also will be positive infinity. So do it on your own and verify it, and you'll see that that will be the case when you approach it via calculus as well. Now let's take a look at rational functions and see their end behavior. Once again, we could use algebra to discuss about how you expect the end behavior to be. So I'm going to talk about the algebra here, and then I will show you maybe one example of these to understand how to deal with the calculus approach. Okay. So for this first one, the degree of the numerator and the degree of the denominator is the same. So algebra, once again, go back to those conditions we saw. You can pause the video, go back and view it, or track it in ebook, OpenStax. So the rule here says, well, you can expect a horizontal asymptote to exist, and that horizontal asymptote will be the ratio of the leading coefficient. So the answer for this should be y equals 3 over 2, just like that. Okay, got that? And then for the degree of the numerator being smaller or lesser than the degree of the denominator, the condition actually says, oh, we automatically know that the horizontal asymptote will be aligned with the x-axis, or y equals 0. Okay. And then for the third one, the degree of the numerator is higher than the degree of the denominator, which means there will be no horizontal asymptote. So we know that there will be no horizontal asymptote. However, the degree of the numerator is one more than the degree of the denominator, right? Just one. They're just 1 degree apart. If that's the case, then we know that there will be an oblique asymptote. And the conditions there said we can find that oblique asymptote using long division of polynomials. And that long division will produce a linear function. And that linear function must be graphed to get the asymptote. Okay, so your graph will kind of be limiting about that slanted line, the oblique asymptote. So we got our answers just like that in a jiffy. But if you're using calculus, what happens is, I will just roughly discuss what happens for each one of them. So if it is limit f of x as x approaches positive infinity, the whole idea is if I have to plug in infinity in the bottom, right? If x is sitting in the bottom and I have to plug in infinity or negative infinity for that matter, what happens is, as I mentioned in one of the examples previously, it's as if you had 1 over 1 over 0, which is the same as 0 over 1, right? Which means the answer comes out as 0. So in other words, if I had 1 over x set up, or in other words, if x is sitting in the bottom, and you're allowing that x to be a very large positive number, a very large negative number, then this will approach 0. So we're going to use that concept, and for all these expressions, we are going to try to move the x to the bottom. Okay, so limit x approaches positive infinity, 3x minus 1 over 2x plus 5. The trick is to divide numerator and denominator by the highest degree of the denominator. Okay, so the highest degree here in this denominator is x power 1, right? So what we're saying is pull out an x in the bottom and on the top. That's what it means by divide numerator and denominator by the highest degree of the denominator. So you always go by the highest degree of the denominator. Okay, that's what we chose. The highest degree was x power 1, which is x. And so that's going to be 3 over, you're pulling out an x, right? Oops, I'm sorry. That does not get anything. This one, you're pulling out an x, so this one is to be divided by x, so that when you distribute, you get back 3x minus 1 because the x's will cancel off. Likewise, here you have 2 plus 5 over x. All right? So these x's will cancel off. We know that. But then as we allow x to approach positive infinity, that is your x sitting in the bottom, right? That means when this x becomes really, really, really large, this fraction will approach 0. This fraction will approach 0. Look at what we're left behind. We're left with simply the numbers 3 over 2. So that is exactly what we anticipated here when I said y equals 3 over 2. So that is what we got. We basically got the limit of f of x as x approaches positive infinity to be 3 over 2, which means the horizontal asymptote occurs at y equals 3 over 2. Okay. Now for the second example, do the same thing. Okay, 3x squared plus 2x. Let's write that quickly. And do the same thing for negative infinity as well. Okay. So this is going to be 3x squared plus 4x over, wait a minute, I'm looking at this one, 3x squared plus 2x over 4x cubed minus 5x plus 7. Okay. The rule says divide by the highest degree you see in the denominator. So we're going to use that rule and pull out x cubed on the top, x cubed in the bottom. The whole idea is to get these x cubed cancelled off. Okay. This move, this is just an algebraic manipulation. This move will work for us always because you're going to push all your x's to the denominator. Okay, so this is going to be, in fact, we need only x squared, but we have x cubed that we're pulling out. So this is going to be 3 over x plus that's just an x. So we just need to balance it off with an x squared in the bottom. So when you distribute it, you get back the x cancelling off with one of the x, giving us an x squared, so 3x squared, plus 2 over x squared and this x cubed. The x squared and the x cubed cancels off, leaving us with one of the x's, so you get back 2x. Okay, and then this would be 4, because the entire x cubed is pulled out, minus 5 over x squared, because we only need a 5x, plus 7 over x cubed. So as we anticipated, the x is sitting in the bottom, so this is going to become 0. This is going to become 0. There is a 4 here. This is going to become 0. It's going to become 0. So ultimately, what this gives us is 0 over 4, right? That's what we're left with. We're left with 0 on the top, 4 in the bottom. So that's going to be simply 0. So in other words, limit of f of x as x approaches infinity came out to be 0, which implies horizontal asymptote is y equals 0. And that's exactly what we expected from section 2. Right? And the third one, you're going to do the long division. So once again, we have 3x squared plus 4x over x plus 2. That's going to be our limit x approaches positive infinity, right? Okay. Now, if you took the largest, highest power from the denominator, that's not going to work here because the numerator is, the degree of the numerator is larger than the degree of the denominator. So that is not going to work. So instead, as much as we try to do that, if we stick to the same rule, what happens then is we have limit x approaches infinity. Oops. You can pull out an x from there, pull out an x from here. That's going to be 1 plus 2 over x, right? And that's still going to be 3x plus 4 over, no, plus 4, because the x was pulled out, right? So then we cancel off these x's, and as we approach x, as x approaches infinity, this one is the only one that becomes 0, right? But then you have an x here, and so when you plug in x as infinity, the answer actually, in this case, it's kind of difficult to use the rule. So there is really no horizontal asymptote because your value comes out to be infinity, right? And it's the other color. So this is, now maybe I can just put it out here. This becomes infinity, right? 3 times infinity. So that's going to be infinity. So the answer comes out to be infinity, as we expected, no horizontal asymptote. However, if we did the long division, we will know exactly how that asymptote works. So the long division really helps you to do 3x. Okay, so multiply that. That's going to be 3x squared plus 3 times 2, 6x. Subtract. That's going to be minus 2x. Okay, so that's going to be minus 2. That will be minus 2x minus 4. Change the sign. We get a 4. So your fraction, or rather rational, will be now written as quotient, which was the answer, this 3x minus 2, that's the quotient, plus this 4, the remainder, over the divisor, x plus 2. Okay, so that is what the condition guaranteed. It said, if this was 1 degree more than what was below, then you will always get a linear function. This is a linear function. In fact, it's a linear function with y-intercept -2 and slope 3. So if you graph this linear function, I'm trying to write linear function here. If you graph this, this will give us the oblique asymptote. This is going to be slanted, isn't it? There's a slope, so it's going to be slanted. So it's going to be like this. And perhaps your graph will be coming really close like this or something like that, so that the slanted line now is your asymptote, which behaves as a limiting function. All right, I hope that was helpful. And I would like you to explore these problems, do as much computation as possible to get comfortable and familiar with handling these long divisions, the powers, and the interpretation of them in algebra versus calculus. Thank you.